Calculus, what's going on? Hope you're doing well. Um, I don't think I should introduce myself. Y'all should know me by now. Mr. Garcia, Mr. Michael, whatever you call me. Today's lesson is over tangent lines and rate of change. So it's really kind of a first introduction to calculus. Now, today is going to be a lot of introduction, so bear with me in this video. Okay, we're going to be doing a lot of exclamation and all these different types of things. As always, with my PowerPoints, every single subtitle will probably be a really bad, cheesy subtitle. For some reason, this came in my head. Let's tango in a line at a steady rate. I, I don't I don't take too much time to think of these. Trust me, I don't. So the first thing is let's discuss what is sorry, not what is, why why should I care about this? One, studying tangent lines will directly lead us into our discussion of limits. Now, same thing for rate of change. They're going to help us understand it. It's going to seem kind of different because I'm going to introduce this concept of tangent lines, and then we probably will never touch on it again in the rest of this UB summer semester. The only reason why is because we don't have too much time. That's it. If we had more time together, we'll be able to spend much more time on this topic. So when you kind of see our question in a bit, you'll be like, oh, okay, I'm ready for that. We actually won't see it again. So, what is a tangent line is the first question. I'm not going to explain it because here's a crazy thing. I still can't believe I pulled this. I really thought that they wouldn't come in time. And yeah, 1 second. Just so excited to come on screen. So I flew him in, and this is very, very, very special guest. So give a round of applause. Let, let me just throw it into him real quick. Let me throw it to him.
Hello, young Padawan. My name is Master Chung Fu, or you may just call me Master S. Now, I travel from a faraway land, a land that many dwell from, a land of Cleveland, and I've come this afternoon to teach you the way of the calculus. And before you understand and learn the way of calculus, you have a lot to learn. You must understand the fundamentals of calculus before you go on any further. We cannot continue until you understand the fundamentals. That is why your teacher, Mr. Garcia, has instructed that I come and teach the way. So first we must discuss what is a tangent line. As you can see on this graph that I have made, this tangent line will be developed and developed more. Now, while there's not an equation for this graph, let's just say it is a function. Okay? Now, a tangent line, I will say it multiple ways. One way for a tangent line. It is a line that touches the graph at one point and is parallel to the graph at that point. Again, this is what that means. I will take a marker that has been handed down for generations and generations. I will take this marker and I will draw this line. It is a line that touches the graph at one point alone. And from there, it is parallel to the graph. Now, one thing I do want to mention, it is tangent to the graph at that point. When I say parallel, that means going in the same direction. Or that we should all be going in the same direction in life. In this case, both the graph and the tangent line are going in the same direction. Now, do not be mistaken. Yes, the tangent line will cross at one point alone, but that does not mean that this over here is a tangent line. That is incorrect. That is the way of the fool. That is not a tangent line. Yes, it is crossing at one point and one point alone. However, it is not parallel to the graph. It is going in a different direction. Now, I must go in a different direction, and I must leave. There's much you have to learn. I understand this road will be tough. It will be difficult. But with hard work and discipline, you can achieve anything except for my rank as Jedi Master, apparently. No. Thank you.
Okay, that was definitely a special guest. So let's just give a round of applause to Master Splinter, Master S. Let's say Master S. You know, he has to travel back to Cleveland this afternoon. So thank you again to him. Hopefully, we don't hear from him again. But you know, I have mass respect for him. Let's review what he said. Tangent line. That is simply put two things. One, it's a line that touches the graph at one point, and two, it's parallel to the graph. Now, what that means is this. They are both being the parallel line, both being the tangent line and the graph. They are both moving in the same direction. So notice here, we're saying we got a tangent line here. The graph is decreasing in this part, and so is the tangent line. And it touches, my bad, at one point. But we don't have a tangent line here. Yes, I know you do cross at one point here, but notice this graph is moving up. It's increasing, while this tangent line is still decreasing. So it is not a tangent line here, and yes, it is here. And cool thing it is, it's a line, so it has our linear equation, y equals mx plus b, you know, shout out algebra 1. So let's look at this example. Find a tangent line to f of x equals 15 minus 2x squared at x equals 1. I'm going to try to write on here, but it may not let me sometimes. So let's find this tangent line. Like I said earlier, it's a linear equation. That means it will take the form, let me see if this will work, y equals mx plus b. So this is good. We know this. We like this. And we also know one thing, again, it's going to touch that graph at one point and one point alone. So that means that x equals 1, that's involved with our function and our tangent line. So here's a cool thing. We already know a point on the tangent on the tangent line. So let's find its corresponding value. My bad. My voice is going away. Get some water. So here, to find our corresponding y value for our x, plug in 1 for your x's. So 15 minus, that'll be 2. So it looks like that'll be 13. Cool. So we know 1 comma 13. That point is on our graph, f of x. Excuse me. And it's also on our tangent line, whatever that equation is. And we're stuck. Because, well, to create a linear equation, you need one of two things. You need either a second point, because with that second point, you can find the slope, and then from there, find the y-intercept, or you just need the slope altogether, really. So that means here is one thing we need to know. What is our second point? And if I have that second point, will that give me the right slope? Will that give me the right y-intercept? Will I even get the right line? And so for the sake of example, I'm going to say, well, what if the second point was x equals 2? Okay, so let's say it was x equals 2. And actually, how about this? I'm going to introduce a new topic. We're going to call it a secant line. A secant line means, let me go to my Desmos graph here. Cool. A secant line means it's just going to cross it at two places. Okay, so let's find the slope of a secant line. So go back to our slides. Let's say x equals 2. So let's find f of 2. Again, to find f of 2, plug in 2 for every place to see an x. 2 squared is 4. 4 times negative 2 is negative 8. 15 minus 8 would be 7. Hey, do you remember how to find slope? Y2 minus y1 over x2 minus x1. So 13 minus 7 over 1 minus 2. So this is saying we have a slope of negative 6. So here, in my equation y equals mx plus b, I know that my m is going to be negative 6. And to find my b value, think back to algebra 1 and algebra 2, maybe even pre-cal. To find your b value, what I can do is I can plug in one of my 2 points. Let's just plug in 113. So that means here, can I pick a different color? I can. Cool. We'll do green. So the point 1 comma 13 is going through this equation. So that means when y is 13, my x is 1. And now look at this. Oh, this becomes just an equation we can solve by itself. So here we get 13 equals negative 6 plus b. To solve for b, we'll move that 6 to the other side. Cool. And now it's very slanted and altogether it's kind of weird to write on this. But this gives us our equation. So this equation, no, it won't be, yikes, that's not good. It won't be the tangent line, but it will give us a good glimpse on how we can find it. So y equals negative 6x plus 19. It's not the tangent line, but let's see what that looks like when we graph it. Y equals negative 6x plus 19. We're kind of, maybe if it took off projector mode, that's a little bit better. We're kind of close. Again, ideally, here is x equals 1. So ideally, we want to touch it there at the graph, and it needs to be a little more slanted. So it's touching the graph again at 2 points, at the point 2 comma 7 and 1 comma 13. So you want to touch at 1 point at 1 point alone. So here's a little GIF here. We need to get a closer slope. That slope of negative 6, it was okay. It was okay. It looked kind of good. But our slope needs to be, I guess, a bigger number. The reason why a bigger number, because then it'll be more slanted. Um, there is a method called approximation, where with this, we can kind of approximate where a slope might be. And so what is happening here is you took that original slope of negative 6, and if we make it smaller, 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 or bigger, bigger, bigger in this case, it will start to tilt the line to be more and more like the tangent line. So what does that mean? What does that look like practically? Is, hey, let's estimate. So here's what we're going to do. We're going to take a whole bunch of different x values, and then from there, find a slope between 1 comma 13 and our new x value. Okay, so we're going to find this slope about 8 times. Just kidding. Well, we are going to do it, but we're going to let the calculator do our work for us. So we are going to find the slope a lot of times. So let's try to minimize all of our work, okay? Let's try to get a formula for the slope. So as a reminder, the slope was our y2 over y1. Change in y over change in x. My y2 minus y1 over x2 minus x1. I said that wrong. But big thing, change in y over change in x. So that means here, let's try to generalize this. So m being slope, it's our change in y, so f of x, minus f of 1. Because I'm going to go ahead and say f of 1 for 2 reasons. 1, because f of 1 is a y value. And 2, I know that f of 1 exists on this tangent line. That's what they gave me. And I'm going to set that over, well, the change in x. So again, this x value, I don't know where it is. But I do know that, hey, I got a 1 as my x values. So what is my f of x again? It was 15 minus 2x squared. And let's subtract my f of 1, which is 13. And well, the 15 and 13 can combine, which be 2. So with this equation, 2 minus 2x squared, what we can do is we can plug in a bunch of values of x to see what is our corresponding slope. Now, I'm going to plug in values of x that are getting closer and closer to x equals 1. So in my calculator, 2 minus 2x squared over x minus 1. With my calculator here, cool. So this is just TI-84 plus CE. I think this is the standard one most people have. Let's plug that in. Let me hide this. Cool. 2 minus 2x squared over x minus 1. Okay. I'm just going to let the calculator do my work for me. I'm not going to, I can if I want to plug in my different values in just my regular screen, but this is much easier because from here I'm like, okay, well, we tried x equals 2 and we saw we got a slope of negative 6. Let's start to get closer. So let's try 1.5. That's in between 1 and 2. Okay, we got a slope of negative 5. Um, I wrote this down in a table, so I'm not going to write it down just yet. What about 1.1? 21, negative 21 over 5, and that worked out to be a decimal. So that's what it's essentially doing right here. Now, I did this already to save us some time. I tried, and I found all these different slopes. Negative 6, negative 5, negative 4.2, negative 4.002. It looks like it's getting closer to a number. How about this? Let's try on the other side of my equation. I'm sorry, the other side of my x value. Let's try on this side. Well, what about the numbers that are getting closer and closer to x? Getting closer and closer to x equals 1, but from the other side. Negative 2, negative 3, negative 3.8, negative 3.998. Oh, huh. So what do you think is happening here? It looks like if we approach our x equals 1 from like the right side, like our big numbers going down, the slope's getting close and close to negative 4. And if we go from the opposite side, the slope's getting closer and closer to negative 4. So what if we tried a slope of negative 4? So let's try that real quick. Yeah, cool. Let's try that real quick. What if we had y equals mx plus b, a slope of negative 4? And again, plug in whatever point. We'll use that point 1 comma 13 to stay consistent. Oh, that's not good. Perfect. Better. Cool. Awesome. To solve for b, negative 4 times 1 is just negative 4. Then add 4 to both sides, so 17 equals b. Therefore, this actually might be our equation. Let's check on the graph, okay? Again, the graph for this should show this line hitting, where's it at? Cool. So show it hitting the graph at one place and be parallel, moving in the same direction. And I had the answer here as well. Oh, it had a different color. But the answer here was negative 4x plus 17. Here's the thing. That took a while. This was a method of estimation, and that's not very intuitive. So we'll discuss a better method later. All right, so a couple things real quick. We looked at points that are happening on both sides of x equals 1. We can never assume that what's happening on one side of a point will also be happening on the other side of the point. All right, I was able to sketch a graph. That's not always the case. Notice as well, I use a lot of points here. I didn't just use like a couple points. I used like 4 points on either side of x equals 1. That's important. You need to use a bunch of points. Couple other stuff. Again, in this case, the numbers were kind of nice. I'm not that mean sometimes. Sometimes your numbers will be quite messier. So you should always use 4 points to get a good estimate. we will discuss a more precise and less, I guess, tedious way to find. Well, ideally, we will be able to at the end of the semester. Hopefully, we will. At the end of our semester, not the school semester. Rates of change. So rates of change. Um, Rates of change are just some variables or originally considered a function that represents some quantity that varies as x varies. So I think the example I give in a bit, is like the rate an air leaves a balloon. It's just some rate of change. So to determine how fast our function is changing at some point, we're going to call this the instantaneous rate of change or just the rate of change of f of x. Now, we're going to estimate. Right now, we don't know how to compute the instantaneous rate of change, but we can find the average rate of change. Now, that should sound a little bit familiar because remember, compute the average rate of change, it's very similar to finding the slope. Change in f of x over change in x. In this case, we're saying x equals a, so I'll say f of x minus f of a over x minus a. Now, to estimate the instantaneous rate of change, we're saying x equals a. We're going to do the same thing like we did last time. We're going to take values on either side of x equals a being just some number, and seeing what are they coming into. So in this case, we have an example of air in a balloon after t hours. So v of t is t cubed minus 6t squared plus 35. And we need to estimate the instantaneous rate of change of the volume after 5 hours. And this question is different. I mean, I don't really give too many units or stuff like that. It's just kind of a broad example. So same thing here. Let me find my average rate of change first. So again, the average rate of change, to find that, is the change in y over change in x. So f of x, let me get my, cool, f of x minus f of a over x minus a. Now, instead of saying f of x, we have v's and t's. So v of t minus v of 5, because our a value is 5, over x, which is just t, minus a, which is just 5. And let's plug in what we know. Well, v of t, we know it's t cubed minus 6t squared plus 35. And what we can find v of 5, I just worked it out. V of 5 is going to be 10. So we did t cubed minus 6t squared plus 35 minus 10. And 35 and 10 can combine. So that'll be 25. Okay, cool. So same thing here. What I'm going to do is I want to find values of t that are approaching 5 on either side. So values that are bigger than t, sorry, bigger than 5, that are kind of decreasing to be 5, and values of t that are smaller than 5, that are increasing to be 5. So t cubed, so I'm going to plug this in my calculator. I'm going to have to go back and forth here, so bear with me. Then now you can do alpha y equals, it says n over d, which is numerator over denominator. And it gives you this nice little thing. Oh, try that one more time. I forgot. I can't really do variables here for some reason. So that's t cubed. It was minus 6t squared. So minus 6x squared. I think it was plus 25. Oop, over t minus 5. X minus 5. Cool. So we're doing the same thing here. So if we start off with 6, okay, it looks like it'd be 25. Same thing here. We'll start off then with maybe say 5.5. We'll slowly get there. Okay, it's a fraction, but we can divide that out in a second. 5.1, and so on and so forth. So here, I did a bunch of numbers just so you can kind of see the rapid rate of change. But with 6, it was 25. 5.5 was 19.75, so on and so forth. And you see here, as it get really, really, really close to t equals 5, I'm getting really close to 15. So that was on one side of t equals 5. Let's try the other side. Let me move my picture all the way. Perfect. So here, 4, 4.5, 4.9, 4.999, so on and so forth. And here, 7, 10, 14, 14.91, 14.991, so on and so forth. And so if you notice on this left side, it's slowly approaching 15. And on this other side, it's slowly increasing to be 15 as well. So that would tell us here, I'm going to try to write it. It's not going to be pretty. I know it won't be, but bear with me. The instantaneous rate of change. Wow, that is nowhere near close to the right word, isn't it? That's supposed to say instantaneous rate of change. Now, it's just 15. Clearly, this needs some units. Clearly, this is just a made up scenario. And honestly, with air leaving balloon, it's not going to be perfect. So there's a bunch of things missing. This is just for the sake of example. All right. But it's changed rate of change to 15 meters per second, feet per second squared. I don't know. Units weren't given. So the reason why we did all that is we're going to try to take what we did with tangent lines and rate of change. So first, we want to find a tangent line or rate of change to f of x at some value of x. For the first question, it was 1. And then for the second question, it was 5. Okay? Next, we knew that the point P, which was 1 or 5, was going to be on that tangent line or with the rate of change. Okay? And then we took a second slope. So I'm basically going to be talking about the first example a lot. We took the second point that was on the graph of the function. So I don't know, just call it Q, whatever. And we computed the slope. So we did that f of x minus f of a over x minus a. And then we started taking values of x that got closer and closer to x equals a. And we looked on both sides of it, okay? And we were looking at this to estimate the slope of that tangent line. And then from there, we said, hey, the tangent line can be found by doing y equals f of a. But this is one of the methods that you could have done, but yes, essentially. So we're going to change the notation. I don't have to put it up here. Just a little bit for the sole reason of being able to use this later on. All right. So I just said the slope was found by using this f of x. Let me get my pointer out. F of x minus f of a over x minus a. And then we plugged in a bunch of x's to determine what's happening. We were just kind of plugging in x's. How far do we go? That's a real question. Let's call that distance of how far we had to go on either side h. So I either had to go from a certain value to the left of it, or a certain value to the right. And just so I stay, consistent, I'll say x equals a plus h and a plus h. Obviously, if it's a negative number, I'm going to say a minus h, but just to stay consistent. So it's important to take both sides, and it's valued is going to be x equals a plus h being some magical number such that it will give me a more precise answer. All right. Now, we can use this method instead of having to guess. So instead of saying f of x minus f of a over x minus a, let's replace all of our x's with a plus h. So f of a plus h minus f of a over a plus h minus a. Again, we replace this x with a plus h, and we replace this x with a plus h. Well, we can't really change anything on this top part. Oh, on the bottom part, hey, we got two a's on bottom. Those can cancel out. We're left with just h on bottom. So let's go ahead and replace the a's with x. We get this final equation. F of x plus h minus f of x over h. This equation will come in handy. Yeah, cool. This equation will come in handy. Now, one thing to note, I know, can I look in the camera? I don't know where the camera's at. I know that was like a lot of what just happened. This is supposed to be an introduction to a thing called limits. With limits, we'll be able to do some more computations easier, but at first it'll be a lot more estimation. Okay? In the meantime, All you need to do was just take notes. You do not have homework over this, but I will see you in class.